to the amplifier. So it reduces the strength. That is a attenuator. So primarily we'll discuss about lattice attenuator is one of the type of attenuator. So it is a general type of a symmetrical and balanced network. Any symmetrical, balanced or unbalanced network can be transformed into an equivalent lattice network. So this figure shows the lattice network, which is terminated with the characteristic resistance at terminals 2, 2 dash. The output is terminated with its characteristic resistance. Lattice attenuator is described by its characteristic resistance and propagation constant. So to derive the expression for characteristic resistance and propagation constant, let us redraw the network as shown in second figure. So if you observe closely the terminals 1 to 2, there is a series arm RA, series arm that is RA, and 1 to 2 dash we have RB, then 2 to 2 dash R0, 2 to 1 dash there is RB. These shunt arms are RB in lattice attenuator, series arms are RA. So it is a symmetrical and balanced network. So we have redrawn this network. Now, if you determine the characteristic resistance, so Z0 is described by characteristic resistance. It's equal to R0 is given by RA into ZOC into ZS. Characteristic resistance for a two-port network is described by ZOC into ZS. So here ZOC means that output terminals is open circuited. ZSC means output terminals that is 2 2 dash are short circuited. In this network, if you open circuit the terminals, this RA plus RB in both the arms are in parallel. So to this RA plus RB, RA plus RB parallel combination is ZOC, that is RA plus RB divided by 2. This is ZOC. And what is ZSC? If you short circuit these terminals 2 2 dash, then what happens? This RA and RB are in parallel here. Here also RA and RB are in parallel. This combination will be in series. Why? Because this is 2 2 dash is short circuit. Then what happens? RA parallel combination. RA RB by RA plus RB is a parallel combination. These two parallel combinations are in series. So we get 2 times of RA RB by RA plus RB. Now find out Z0. What is Z0 now? Z0 is square root of ZOC RA plus RB divided by 2 into 2 RA RB divided by RA plus RB. So this 2 and 2 gets cancelled. RA plus RB gets cancelled. So what is remained is only square root of ZA into ZB. So for a lattice attenuator, the characteristic resistance of lattice attenuator is nothing but square root of RA into RB only. It's the geometric mean of this series and shunt arms. I can easily remember square root of RA into RB. Now, to determine the propagation constant alpha. So how to determine the propagation constant? Let us apply KVL to this network. Before that, give the notation. So this is current I1. If this current is I, then the current which is divided here. So this is I1 minus I. Let us consider this is I2 in the two-port networks. So what is this current now? I1 minus I minus I2. Here the current I is coming and I2 is also coming. So I plus I2. Now consider the path 1 to 2, 2 to 2 dash, then 1 dash. This is the path. This is the path we are considering. Closed loop we are considering. So what is this? Voltage is V1. Let us consider. Source voltage is V1. Now, what is the KVL equation now? Apply KVL to the network. Apply KVL to the network. One to two to two dash, then one dash. What will get? V1 is I1 into R0. We know that it's equal to RA into I1 minus I plus I2 into R0 plus R0 into I2 plus RA again RA into I plus I2. So if you expand this, write I1 terms one side and I2 terms on the other side. So if you take I1 as common, here is RA into I1. So we get R0 minus RA. What is the other term that is remained is minus RA into I plus take I2 as common. So R0 plus RA plus RA into I. This plus RA into I minus RA into I gets cancelled. Now we require the ratio I1 by I. With this, we can determine what is the ratio of the propagation constant alpha. Now, what is I1 by I2? I1 by I2 is R0 plus RA divided by R0 minus RA. This can be written as 1 plus dividing the numerator and denominator with the characteristic resistance R0. So we get 1 plus RA by R0, 1 minus RA by R. So this also can be written as 1 plus square root of RA by R0. These ratios are nearly same. So this is for notation only for the convenience. We are taking this square root. So there is no change in this ratio, even though if you consider the square root. Now, what is the propagation constant? N is represented as N is in Napier's. So e power alpha is nothing but I1 by I2, which is 1 plus square root of RA by R0 divided by 1 minus square root of RA by R0. Finally, we can write what is alpha is ln of taking anti-logarithm on both sides. We get ln of 1 plus square root of RA by R0 divided by 1 minus square root of RA by R. This represents the propagation constant of lattice attenuator. So to describe lattice attenuator, we need the characteristic resistance, that is square root of RA into RB, and its propagation constant alpha, which is natural logarithm of square root of RA by R0 by 1 minus square root of RA by R. So we can represent this RA and RB in terms of its propagation constant. So here we have N. We are saying N is I1 by I2. This we are seeing it as R0 plus RA by R0 minus RA. If you cross multiply and simplify this, we can get what is RA. What is RA? N into R naught minus RA equal to R naught plus RA. So from this, we arrange the terms so that RA, if you take it as common, RA into 1 plus N or N plus 1. We take R naught as common, we get R naught into N minus 1. So what is RA now? RA is R naught into N minus 1 by N plus 1. Similarly, we can represent RB as R naught into N plus 1 by N minus 1. Here N is greater than 1. So these equations can be used to find the equivalent lattice network for T and pi networks using bisection theorem. Let us define what is the bisection theorem. So a network is said to have been bisected when the open circuited and short circuited input impedance of the two bisected networks are equivalent. Also, the square root of the product of impedances is the characteristic impedance of the original whole network. This is the bisection theorem. So no need to confuse. We will simplify this. The bisection theorem states that any symmetrical balanced or unbalanced network can be transformed into an equivalent lattice network. The series sum of the lattice network is equal to the short circuited impedance of the bisected network, and the diagonal arm is the open circuited impedance of the bisected network. So it is very clear. So what is its series sum? Series sum is when we bisect the two-port network. The series sum of the lattice network is equal to the short circuited impedance. Short circuited means output port of bisected. Any one of the bisected network is short circuited. We can determine its equivalent impedance. And the diagonal arm is the open circuited impedance of the bisected network. Let us see. So bisection theorem is clear. So let us consider T-type attenuator. T-type attenuator. So based on this bisection theorem only, we will classify this T-type and pi-type attenuators. So a T-type attenuator is a symmetrical but unbalanced network. How to represent the T attenuator is? It is symmetrical but unbalanced network. So this we consider as R1 by 2. This is R1 by 2. So it can be said as symmetrical, but it is unbalanced. So according to bisection theorem, we'll bisect the network into two halves like this. This is R1 by 2, no change. This we'll write it as 2R2. Why we are writing it as 2R2? Let us see. This is one bisected network. Another bisected network will be like this. This is also 2R. If you join this bisected network, we'll get this original network. So this 2R2, 2R2 parallel combination, that is R2. If you combine this, we'll get this is T attenuator, T-type attenuator. This figure shows the bisected network. Bisection of P-type attenuator. P-type attenuator. Now, according to bisection theorem, we can represent this a series arm of lattice network is equal to the short circuited input resistance of the bisected network, and the diagonal arm is equal to open circuited input impedance of bisected networks. So here if you consider, let us consider any one bisected network. So let us consider the first one. This is R1 by 2. This is 2R. Now, these are the terminals 2, 2 dash. This is 1, 1 dash. This is 2, 2 dash. Now, what is its short circuited impedance? So, ZSC is equal to the series arm. If you short circuit these terminals, what happens? This 2R2 will be combination with short circuit. So, this is negligible. So, RA simply is equal to R1 by 2. And what is its diagonal arm? That is RB. RB is the open circuited input resistance of the bisected network. What is its open circuited impedance? This is R1 by 2 plus this 2, 2 dash is open circuited. So R1 by 2 plus 2R2. This is a open circuited resistance, that is RB. So now we have, whenever we get this RA and RB, we can draw the lattice network. Lattice network, right? So we know for a lattice network. So from lattice network, this RA is nothing but R naught into n minus 1 by n plus 1. RB is R naught into n plus 1 by n minus 1. So solving these two equations for this T-type attenuator, we get this R1. Let us consider this is R1 for T-type. R1 is 2 R naught into n minus 1 by n plus 1. And this 2R2. 2R2 is R naught into n plus 1 by n minus 1 into, sorry, minus n minus 1 by n plus 1. So if you solve this equation, we get R2 is R naught by 2 into 4n by n square minus 1. So this we get 2n into R naught by n square minus 1. These are R1 and R2 for this T-type attenuators. So R1 is 2 times of R naught into n minus 1 by n plus 1. R2 is 2n into R naught by n square minus 1. Square minus 1. Similarly, let us see the pi-type attenuator. You see the pi-type attenuator. So a symmetrical pi-type attenuator can be like this. One dash. This is 2R2. This is R1. This is 2R2. This is 2 dash. Now, if you bisect this pi-type attenuator, what we'll get is this is remain 2R2 only. 2R2. This R1 is divided into R1 by 2 in one bisected network. In another bisected network, this is R1 by 2. This is same to R2. This is a bisected network. So this is figure A, pi-type attenuator. Pi-type attenuator. Figure B shows bisected network or pi-type attenuator. Bisected network. So the definition remains same. This pi-type attenuator can be represented as a lattice network. So from the definition of bisection theorem, the short circuited impedance gives the series arm and open circuited impedance gives the shunt arm or the diagonal arm. So for this pi-type attenuator, this RA is short circuit. If we short circuit this 2R2 parallel with R1 by 2, we'll get R1 by 2 into 2R2. So R1 into R2 by R1 by 2 plus 2R. This is the parallel combination. Then what is RB? RB is open circuited impedance. So it is simply equal to 2R2. What about this R1 by 2? This is open circuited in series with the open circuit. So no need to consider this R1 by 2. Again, from lattice network, from definition of lattice network, we know the expressions for RA and RB in terms of propagation constant. RA is R0 into n minus 1 by n plus 1. RB is R0 into n plus 1 by n minus 1. So for this pi-type attenuator, and solving these two equations, set of equations, we get R1 is 2 RA RB by RB minus RA, it's equal to R0 into n square minus 1 by 2n. And what is R2 is RB by 2. What is RB here? R0 by 2 into n plus 1 by n minus 1. So these are the distances R1 and R2 expression for pi-type attenuator. These two are for T-type attenuator. So finally, we have seen the lattice attenuator, general type, and from bisection theorem, any attenuator can be represented in terms of lattice network. So we have seen T-type attenuator and pi-type attenuator. Both can be represented as a lattice network. Okay, thank you.